Okay, hi TFA, this is Miss Yam. How are you? And I am on a field trip with my multivariable calculus class. And so today you are going to be having this lesson via screencast. So the purpose of this lesson today, of our topic today, is to introduce you to a new unit of measure for angles. And one of the things that I talked to you about, I think in class, I don't remember what day it was, is that when we have an angle, the unit that we are most comfortable measuring angles in is degrees, right? Theta degrees. And that makes sense. I mean, this theta degrees is kind of a measure of this arcness, or the way this thing opens. If you think back to your protractors that you used back in the day, that little kind of like semicircular thing, right? Where you place the vertex, which is the corner, by the way. The vertex of an angle is this corner. You put the vertex of the angle there, right? And you'd kind of line up one of these sides with the initial side of the angle. And then you'd kind of see, right? You'd line up, you'd see where the terminal side intersect the protractor, and right around here there'd be a degree measure, and that degree measure measures that angle, right? So degrees are so ingrained in you. Measuring angles by degrees, you can visualize a 90-degree angle, you can visualize a 180-degree angle. Degrees are such a part of what you've been doing with angles so far. But what I'm going to introduce to you today is another way of measuring angles. And instead of using degree measure, we're using radian measure. Okay, and I'm particularly interested in some of you who may have seen radian measure to see. Hi, Mr. Cronin.
What's up?
As I had in my pre-cal class.
Hola. Divide by pi.
Sorry, I had to pause you because Mr. Cronin was distracting me with his nonsense. But I'm interested, Sam, to see what you think about how this explanation of understanding what it means to be a radian measure is. A lot of people know how to convert between degree measure and radian measure. Very few people understand actually what radian measure means. I know you all know what degree measure means because the fact that you can so easily visualize a 30-degree angle, the fact that you can make, with approximate accuracy, like a, 90-degree angle with your hands tells me that you understand, almost without you having to think about it, what a degree measure is. All right, so let's begin. Here's what I'm going to do. I'm going to put a circle around this angle. And your drawing is going to be better than mine. But I'm putting a circle around this angle in a way that the center of the circle is the vertex of the angle. Okay, so that is deliberately and must be the center. And please don't laugh at my circle. I realize it's kind of bulbous and embarrassing. So the heart of radian measure stems from this idea. The idea that while we can use a degree or degrees to measure this angle, I could also measure this angle and think about it and measure it in terms of the length of the arc that it cuts. Technical word here is the length of the arc that this angle intercepts. This distance here on the circle is called an arc, okay? And as you see, this angle intercepts an arc. An arc, some people like to say, is kind of a portion of a circumference, right? It's obviously not the whole circumference, but it's a portion of the circle's circumference. And I think it's fair to say that if this angle theta was smaller, the arc would be smaller. If the angle theta was larger, the arc would be longer. The point here is that, would you agree with me that, let's say this angle, if this angle was, say, 6 degrees, this length of the arc that's intercepted, right, would be unique to the fact that this is 6 degrees. So the heart of radian measure stems from the idea that maybe there's a way that we could measure this angle, not in terms of how much it opens per se, but the length of the arc it intercepts. What the hell happened to my paper? Okay, sorry about that. So the point is that the length of this arc is unique to this angle, okay? However, some of you more astute ones there would say, well, Miss Yam, you drew this circle to be this shape, What if the circle was this shape, right? And this circle still has a center. And again, please, I'm sorry. The center here is still the vertex, but then you'd say, clearly, this arc is shorter than this arc. And I can even exaggerate this and say, like, what if I made the circle like this, right? What if the circle was like this? Again, still the center, and still the same angle, but take a look. This arc is clearly shorter than this arc, which is shorter than this arc. So hopefully you're saying to yourself, Miss Yam, you've been talking about the fact that I could describe the intercepted arc as unique this angle theta, but how can that be true if the length of that arc is actually different depending on the size of the circle that you draw? And that is exactly where I want to lead you now. You are right that the length of the arc is different. However, here is what's the same, believe it or not. While the length of the arcs are different, the number of radius lengths that the arc contains is the same, regardless of the circle. What do I mean by that? Let me give you a clean drawing. Okay, let's say here's theta. This is theta degrees. And let me redraw a circle here. Okay, and again, the center must always be the vertex. Now here's what I want you to think about. Instead of actually asking you to think about the length of this intercepted arc, and by the way, that word intercepted is spelled this way, intercepted arc, okay? The arc kind of cut by that angle. I want to ask you this, just eyeballing it, even using my drawing or the drawing that you use, right? When I put this circle here, I create what's called a radius, right? This is a radius length after all. I would love to ask you, I know that the arc is bent, I know that the radius is straight, but just eyeballing it, how many radiuses would you say are in this arc? One radius, a little less than one radius, a little over one radius? I mean, by my drawing, I would argue that this arc is a little less than one radius length. Okay, would you agree with that? In fact, if I'm eyeballing it, I'd say maybe it's like 0.8 radius lengths, 0.8 radius lengths. Okay? And the number of radius lengths in the intercepted arc, boys and girls, doesn't change if you change the circle. So let's make a really teeny circle right here. And again, here is the intercepted arc, right here. That's the intercepted arc. Now, when I make the circle like that, look at this radius. I'm going to ask you again, how many radius lengths do you think fit in this arc? How many of these would you eyeball are in this length? Again, a little less than one, right? So while the actual length of the arc will differ, the number of radius lengths in that arc does not. And that is the key to understanding how to describe an angle using radian measure. So let's write that down. Okay, so I'm in the dining hall and they just put on AC/DC. So if you hear that background music, that's what that is. Okay, so here's the statement I wrote over here. An angle theta intercepts an arc, right? Clearly. And while the actual length of the arc will change depending on the size of the circle, as we just talked about, the number of radius lengths of that arc is constant. So looking at my picture here, right, we said this arc is about, 0.8 radius lengths, right? But so is this arc. This arc is about 0.8 radius lengths. That's what I mean by this statement right here, right? While the actual length of the arc will change, the number of radius lengths of that arc is constant, okay? Huge, huge statement. This is what it means to understand the relationship between an arc and a radius, right? So if we look at my picture here, it's kind of a big moment. If we look at my picture right here, and I know that the way you drew it, it may be different, but I'm just going for what I drew right here. If we look at this picture here, I could describe this angle theta two ways. I could call it theta degrees. This is my old perspective, the old comfortable one. I could describe it theta degrees, or I could describe it as an angle that intercepts an arc whose length is about 0.8 radius lengths. Okay? As an angle that intercepts an arc whose length is about 0.8 radius lengths. I hope you're looking at these two and saying, there's got to be a shortcut to this. Look how short this is, theta degrees. An angle that intercepts an arc whose length is about 0.8 radius lengths. This is how you write this. You capture this whole idea by calling theta 0.8 radians. This word right here, radians, people toss it around all the time. If you go to a party, everyone says radians, 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 radians. Does someone actually know what 0.8 radians means? It means the angle intercepts an arc whose length is about 0.8 radius lengths. This word is this paragraph, okay? So I could say that theta is, and because I don't have a protractor, boys and girls, but if I had a protractor, I'd actually put it on top of my screen here and try and measure this angle and get the actual degrees. So, I don't know, maybe it's like maybe 70 degrees. Let's just kind of maybe just say that, okay? So, I could say that up above, theta equals 70 degrees. Or I could say theta equals 0.8 radians. That R means radians. Okay? Here's where I'm going to be really, really picky now. Well, I think I always am picky, but you know, when you mean degrees, you have to have a degree symbol. You can't do that. You just can't just write 70. And I'll tell you why. Theta equals 0.8 radians, but guess what? More often than not, the R is dropped. So 0.8 radians, 0.8 R, or 0.8 with nothing here, no degree symbol, no R. The understanding is degrees, radians. So very important now. If you wrote 70 and you didn't have this little circle up here, right? If you just wrote 70, some would say, oh, it's 70 radians. 70 radians? Boys and girls, think about it. Is 70 radians a larger angle than 70 degrees? Let's think about it. An arc that would have 70 radius lengths. Oh my goodness, let's think about this. Here's one radius length. Okay, so an arc would be, here's 1, 2, oh, absolutely. 70 radians is a much bigger angle than 70 degrees. All this is saying now, just to be very clear, and I know I'm possibly beating a dead horse, when you mean degrees, you must put the degree symbol. If you don't have the degree symbol, guess what the assumption is going to be correctly? It's going to assume radians. Okay? So now I lead you to possibly the most epiphanous moment. You have been told, and you probably know, the circumference of a circle equals 2 pi r. Okay? Do you have any idea why this is so powerful now? What this is saying is that in a circle, right? In a circle, if you have a radius here, the circumference, which is the distance around here, that length equals 2 pi radius lengths. Okay, which is approximately 2 pi is 6.28 radius lengths. So believe it or not, you've been actually thinking of radian measure for quite some time. What this is saying is that for any circle, regardless of the size, regardless of how large the radius is, the distance around is exactly, and will always be, about 6 1/4 radius lengths. You can even eyeball it if you want to, right? Here's one of them, maybe. Here's about 2, 3, 4, 5, about 6.25, right? Roughly, okay? So again, when we think about radian measure, one of the things you have to fundamentally understand, this is for everything, frankly, is that not just the ability to just know how to take an angle and convert between the two perspectives, but radian measure comes from a unique perspective, which is, let's change the idea of conceiving of an angle from this kind of degree of opening to looking at how that angle intersects with something else, a circle, and namely how that angle intercepts an arc. And what we find is radian measure offers you a new perspective. And that perspective is thinking about the length of the arc intercepted. And as with everything, and you hear me say this over and over again, a new perspective is initially going to feel uncomfortable. A new perspective may make you feel like, what is the point, right? However, I want you to just lean into that and embrace this new perspective. 6.28 radius lengths corresponds to, okay, sorry about it. 6.28 radius lengths is the circumference. So here's my question. So here's a question I want you to ask someone right now next to you in class. You can ask yourself. What angle in degrees do you think corresponds to an intercepted arc of 2 pi radius lengths? If you want to take this all the way on your own, you can just pause me here and then replay me when you have an answer. If you want to walk through it with me, you certainly can. Let's see. Let's talk about an intercepted arc first. So here's this circle here. I'm going to go in there and just put in an angle, okay? And I may change it, but let's just start there. So the angle's vertex to the center. Here's one initial side of the angle, here's the terminal side. Well, let's see, this angle, theta, right, intercepts this arc right here. But I want the arc intercepted to be 2 pi radius lengths. Well, 2 pi radius lengths corresponds to how big of an arc? The entire circumference. So what I want to do is, I want to look at this and say, I want the intercepted arc to encompass all the way around. So my terminal side and my initial side are going to overlap, right? So look at the arrow. The initial side of the angle opens up all the way around. And what's the length of the intercepted arc? It is this entire circumference. So I guess one of you could say, like, well, the intercepted arc is the entire circumference. Yes. So here's the question, back to the question. What angle theta corresponds to that? Theta equals 360 degrees. What angle in radians corresponds to 360 degrees? Let's go back. Radian measure means the length of the arc in terms of the number of radius lengths. Let's see. How many radius lengths are in this arc? 2 pi. So theta equals to 360 degrees is equal to theta equals 2 pi radians. Again, when you write this, what you are saying is, I'm looking at an angle where if I place its vertex in the center of a circle, the arc it intercepts will be 2 pi radius lengths. And here is your first equivalence between a degree measure and a radian measure. 360 degrees equals 2 pi radians. Okay? And from here, we can play a whole bunch of games, right? I mean, I can say, well, if 2 pi radians is 360, how many radius lengths is 180? If I open this angle, start here, end here, right? The intercepted arc is right here. How many radius lengths are in that intercepted arc? The entire way around is 2 pi, then 180 degrees is equal to 1 pi radian, or just pi radians. Okay, sorry. I actually went and asked if they could lower the music, but apparently they can't. And I guess listening to, I think this is Bananarama is is a good thing in the morning. All right. So now you have your first, like, automatic, 360 degrees is 2 pi radians. And all I'm going to do here is, all I'm going to do here is oh dear, what happened? What just happened? What exit this? Oh, good. All I'm going to do here is I'm going to erase this because I want to make room between 360 and 180, okay? So we know 360 is 2 pi radians. You know 180 degrees is 1 pi radians, okay, or pi radians. Well, let's cut that in half again. What do you think 90 degrees would be in radians? It'd be 1/2 pi, or pi over 2 radians. I'm going to start dropping the r. And then you know that half of 90 degrees is 45 degrees. And now we're down to pi over 4 radians, right? And let's see, if 90 degrees is pi over 2, let's go to the side here. 30 degrees is a third of 90 degrees, right? So 30 degrees is a third of 90 degrees. So what would a third of pi over 2 be? Because I want to convert 30 degrees to a radian measure. Well, 1/3 of 90 is 30. What's 1/3 of pi over 2? Yes, 30 degrees is pi over 6 radians. What do you think about 0 degrees? Yes, a 0 degree angle intercepts an arc that has 0 radius lengths in it. And let's see, so our good friend 60 degrees. Let's see. Well, if 30 degrees is 1 pi over 6, 60 degrees is 2 pi over 6s, or pi over 3. So why did I break this down like this? Well, we know where this came from. It's just some mental math and fraction work to get us down here. But you want to know why I brought us all the way down here? Well, because here we have those 3 angles that are so near and dear to our heart. Okay? And we can now talk about 30 degree, 45 degree, and 60 degree angles by their radian measure. Okay? So right now, and I guess when I say now, I mean like today and tonight, I'd love for you to start thinking about 30 degree angles. Oh, but a 30 degree angle is just pi over 6 radians. Okay, and actually I want to try a little mental experiment with you. Let's see. You can watch me draw first. This is 90 degrees, right? This is 90 degrees. I use the little grid lines to help me. I'm going to put a circle around it just because I'm curious. And I'm going to try to be really accurate. I think I'm pretty good right now, right? It's pretty good. And how do I know I'm pretty good? Because I'm trying to use these grid lines, right? Because if this is the center, one to here, I just chose like points to make this a perfect circle. Here's my question. Let's see. This radius length, it's 3. That's interesting. So if 90 degrees is pi over 2 radians, and pi over 2 is roughly 3.14 over 2, or roughly 3 over 2, or roughly 1.5. What this tells me is that in this intercepted arc, there should be about 1.5 radius lengths. And if I eyeball this, boys and girls, look at this. Here's 1 radius length, and about, if I could cut the paper out and like straighten this length, this arc, my logic test is it's passing my logic test. Like, this looks to be about like, here's about 1 radius length and a half, 1.5 radius lengths. So this radian measure of pi over 2 radians makes sense. I'm going to also do this. Let's put in a 30 degree angle. Again, I'm not being perfect. I don't have a protractor on me, but see, that's 90. This is 45, right? So 30 is going to be maybe like this. Okay, so here's a 30 degree angle. This is 30 degrees. Okay, well, let's look at the intercepted arc right here. Right here. Now, if 30 degrees is pi over 6 radians, pi over 6 is about 3 over 6, which is roughly, what? A half, right? Roughly a half. So in this intercepted arc, there should be roughly a half of a radius length. And again, look at this. Here's the radius length. This looks to be a half of a radius length. Okay? So the purpose of this screencast here is to not only introduce radian measure of angles to you, but for you to really understand where radian measure comes from. Okay? Radian measure of an angle comes from the idea that while an intercepted arc's length will differ, the length will not differ if you conceive of it in terms of radius lengths composing that arc. Okay? Fantastic.